My name is Julia Matevosyan. I'm an ESIG Chief Engineer. I would like to welcome you to our 2024 ESIG monthly webinar series and give you a little bit of background on ESIG. For those of you not familiar with ESIG, we are a membership-based nonprofit organization providing our members with objective information, resources, and networking opportunities in support of the energy transition. We do this through workshops, tutorials, webinars, blogs, working group, and task force activities, and producing technical resource materials. If you are new to ESIG and you like what you hear, I strongly encourage you to follow up with us, and I think you'll be pleasantly surprised. ESIG membership gives you an opportunity to participate actively in all of our working groups and task forces. You can find more information about us on the web at www.esig.energy, as well as on LinkedIn, Facebook, Twitter, and YouTube. ESIG also serves in a leadership role with the Global Power System Transformation Consortium, or GPST, whose mission is to bring together key actors to catalyze a rapid clean energy transition at unprecedented scope and speed. ESIG leads Pillar 1 out of 5 pillars, which deals with research agenda for the system operators. More information on GPST can be found at www.globalpst.org. Okay, just a few logistical matters before we get started. The phones will be muted for the duration of the webinar to avoid unnecessary distraction. For the Q&A, as usual, we're using Slido platform. So to ask your question, please go to slido.com and enter ESIG10 as an event code. The instructions also will be posted in the chat. You can also see thumbs up button next to the questions, which allow you to cast your vote and help us prioritize questions that are submitted. We plan to save about 10 to 15 minutes for the Q&A at the end, and then wrap up at the top of the hour. An email will go out with a link, and the link will be provided once the video file has been posted. We also plan to provide short responses to all unanswered questions after the webinar, so please don't be afraid to ask your question through Slido. And the event code is ESIG10 again. All right, so to introduce today's topic and speakers, frequency performance is one of the major aspects for ensuring safe operation of power industry as power industry moves towards high renewable future. Understanding how inverter-based resources change the frequency dynamics, identifying potential regional inertia risks, delivering IBR fast frequency response stably, and maintaining satisfactory frequency performance are critical aspects for a safe and reliable transition towards high IBR systems. This webinar will introduce EPRI's latest work on inertia recognition analysis, regionalization analysis, IBR frequency response stability screening, and bulk power system frequency performance assessments. I would like to welcome today's presenters, Parag, Mitra, Deepak, Ramasubramanian, and Chengwen, Zhang. Just to introduce the speakers, Dr. Parag Mitra is a principal technical leader with EPRI, where he leads the research areas of power system modeling and model validation, probabilistic long-term transmission planning, and integrated strategic system planning. Dr. Mitra holds PhD in electrical engineering from Arizona State University and BTech degree in electrical engineering from Malviya National Institute of Technology in India. Dr. Mitra is a senior member of IEEE. Deepak Ramasubramanian is a senior technical leader at EPRI. His work at EPRI includes development of new and improved mathematical models and processes for the large electric power system to represent the behavior of inverter interface generation resources and loads, and evaluation and development of transmission planning criteria, including uncertainty of sources and loads. Chengwen Zhang graduated from University of Tennessee with his PhD in electrical engineering. He is currently an engineer and scientist with EPRI. His research includes power system inertia and frequency dynamics, PMU-based controls, and data analytics, hardware-in-the-loop simulations, and microgrid operations and control. So again, just a short reminder before we get started, use Slido for your questions at slido.com with an event code ESIG10. And without any further ado, let's go ahead and get started. Parag, Parag, Deepak, Chengwen, I turn it over to you.
Thanks so much, Julia. I'll just give a quick introduction to set the topic up and then hand it over. So we've been hearing a lot about the way the system is changing, how frequency performance might change in the network with inverter-based resources, aspects related to inertial energy injection, and what kind of changes may occur because of that. So for the past few years, we've been doing work trying to get an understanding of how does a large interconnect break up into different regional inertia clusters? Is there a difference between having a single largest in-feed loss on the entire system versus a local in-feed loss that might cause a greater impact on the network? And how do you identify those boundaries and how do you mark out those regions? We've been seeing a lot regarding fast frequency response come up, but we also know that fast doesn't always mean good, or fast doesn't always equate good. So then the question is, okay, at a particular node in the network, how fast can fast frequency response be? And how much of fast frequency response can be injected at that particular node? And are there ways to evaluate and identify those metrics? We'll talk a little bit about that. We'll talk a little bit about some of the clustering work that we've been doing to tie all of this together, try to get an understanding of when you compare system strength, when you compare rate of change of frequency, when you compare inertial energy injection, how does that all come together in trying to get an understanding of system resources and the way in which they'll behave? We'll talk a little bit about a few case studies that we have done to help identify and get a little bit more detail into this. So a lot of material, talking a little bit on theoretical background, talking a little bit on an application side. Please feel free to keep throwing the questions in Slido. And Parag, you want to say a quick few words?
Yeah, thanks, Deepak. You already covered most of the important things. Like Deepak said, yeah, these are kind of now looking at some of those emerging questions that are coming up with high amounts of ideas on the system, how you control frequency, how you should be doing frequency response studies on your system. There are implications on that as well. So definitely interesting topics. I won't take away a lot of time from the presentation, so I'll pass it over to Ham, who has been the lead engineer who worked on all of these things. So Ham, take it away from here, and we'll be online looking at the questions on Slido.
Right. Yeah. Thank you so much, Parag, Deepak, and Julia for the introduction. Hello, everyone. My name is Chengwen. Some of you may also know me by the name Han. I'm a engineer scientist at EPRI that work with Parag, Deepak, and Vikas on these frequency and inertia related topics. So today, we're going to share with you some interesting results we got recently out of the work. We are going to cover three major topics. The first one is the inertia regionalization and local frequency dynamics, and then frequency response deliverability screening for IBRs delivering strong frequency response from weak regions. And lastly, we're going to share some interesting results out of a project that's a collaboration between EPRI and our utility member SRP, Salt River Project, the utility in Arizona. Okay, for those of you who are not very familiar with the frequency dynamics, here are two very quick primary slides to get you up to speed. So in traditional power systems, we have generators, a large number of generators rotating at a constant speed in steady state. And we can look at them like the cars moving at a constant speed on a road. But when it hits a curb, hits a slope, you have to climb that slope. You will encounter some decelerations in the car. So in this stage, there are two main things happening. The first thing is the inertial energy within the car that's due to the vehicle mass. And another thing is you're going to probably step on the gas pedal to have the car maintain a speed or even accelerate. It's a very similar situation in power systems. If you look at the figure on the right, in steady state, the frequency is ideally at the nominal frequency 60 hertz, but when there is a disturbance that causes a power imbalance between the generation and load, you're going to see the frequency decline. And at the first few moments of decline, we define that slope as the rate of change of frequency or roll-off. And then there are going to gas pedals being stepped on, and then you're going to see the frequency finally will return to a new level, settle at a new level B here. And in this process, you're going to reach the lowest point, C, that's called frequency nadir. So we want the frequency nadir to not dip too low because there are under frequency load shedding thresholds and other mechanisms to keep the system stable. If you cross those mechanisms, thresholds, the system might have to shed loads or there will be subsequent consequences. So these are some basic concepts during the frequency dynamic. And as I said, there are two major kinds of responses. One is by the physics, the inertial energy with the vehicle or the generators. And the other type is the when you step on the gas pedal in power system that consists of a few types of control. First, there are fast frequency control. We're looking at more and more of these from the fast reacting resources like IBRs, and it can also come from fast load shedding schemes. And traditionally, we have the other three types of frequency response. That's the primary, secondary, and tertiary frequency control. Basically, the primary frequency control is to stabilize the system at a new level, and the secondary frequency control brings this system frequency back to the nominal frequency of 60 or 50 hertz. And then there's a longer term tertiary frequency control to optimize the power flow across the interties. This figure on the left bottom here shows the rough time scale of these responses. You're going to see the initial response first, and then the fast frequency response, then the primary, secondary, and tertiary frequency response. A quick note here, this is an additive figure. The curves here are for demonstration of the time frame of different responses only. So the shape of the actual curves depend on the control mechanisms in the power system and the devices. So with these frequency dynamic basics, let's get into the three topics we would like to cover today. The first one is the inertial regionalization and local frequency dynamics. So when we think of regional frequency dynamics and regional inertia, I always like to start with the single machine infinite bus system. And you can see here is a generator on the left. It has an inertia constant of H. It's connected through an impedance to the system bus. And the impedance or admittance here is noted as B. So the two things that really dominates the dynamics of this generator can be explained by the Swin equations here on the right. So you have the two factors, the inertia constant H and also the connection strength B. So if you have both of them at a very high level, which can be true for most parts in traditional power systems, then you can expect this generator to move pretty coherently with the rest of the system when there is a frequency disturbance. But if you see inertia decreasing or the connection strength to be insufficient, you can expect this region or this generator to behave a little bit differently or even more drastically different from the rest of the system. And on the left here is an example we did on the Great Britain system. There, we divided the system into 4 regions and applied the same amount of disturbances. And you can see in the northern part of the interconnection, which is noted by these green curves, you can see those very drastic regional local frequency dynamics when the disturbance happens. And this is exactly what we want to focus on this inertial regionalization topic, because inertia is not distributed evenly across the system, and you can have weakly connected regions with low inertia, regional inertia levels. And nowadays we have more and more IBR integration. If they're concentrated in the same location, that can also pose more risks on that region to have lower inertial levels, and these dynamics may not be captured fully in traditional interconnection-wide frequency studies. And here is an example that we did this year with our member SRP on the collaborative inertia and frequency study project. In this example, it shows very well how regional dynamics can pop up in the system. We had a disturbance in the almost southern tip of the Wecker interconnection in Arizona. This is a large disturbance of 2,800 megawatts. But actually, the worst frequency nadir occurred way up high in Canada, in Alberta, Canada, and that's thousands of miles away. And you can see in the curve on the left, after disturbance, we see the frequency measurements in SRP region and also a lot of buses in California. They started to decline first because they are closest to the disturbance. And the two curves that started to drop later, those are measured in Alberta, Canada. And it's understandable because it's electromechanical wave propagation that takes time to spread to Alberta. But when you look at the frequency nadir, when the nadir happens, it's actually the generators in Alberta, Canada that gave us the lowest frequency nadir. And this phenomena will be explained in the later slides when we get deeper into this inertia regionalization analysis. So now we know the inertia is not distributed evenly across the system. You can have very strong regional dynamics. We want to be able to screen regions with very high regional frequency dynamic risks or low regional inertia risks very rapidly, instead of doing thousands of time domain simulations without a clear clue where will be the riskiest region. We developed this method to use only the very basic network data to do the analysis. The idea is to first take in, as I said in the previous slides, the two major factors. The first is the inertia constant of the generators. So we're going to take in the generator dispatch information and inertia constants that tells us how the inertia is distributed across the system. And then the second information we take is the basic network data that tells us how the generators are actually connected to each other. And once we have these two pieces of information, we form an extended matrix and use a technique called Cron reduction. The idea is to reduce the size of the matrix because for a large interconnection, you can have thousands of buses, and a lot of them are not generator buses. We don't focus on that. So we want to get rid of those buses, but still hold the dynamic interactions between the generators. This is what the Cron reduction does. Once we have the reduced matrix, we apply the spectral clustering technique. And what this clustering will tell us is what are the generators that tend to behave coherently with each other, so that in the disturbance, they will move together with each other. But between the clusters, they may exhibit larger differences in their transient behaviors. And once we have this, we will know how many clusters or groups of generators are there in this interconnection. And for each of the regions, we will be assessing their risks for regional inertia issues. And we came up with a metric called AM metric, which I'll show a bit more in later slides. So this slide shows a bit more detailed process of this. You take in the different matrices. If there are topology changes, you update the matrix, and then for the regions, and for each of the regions, we do metric evaluation that takes into consideration the largest disturbance in the region and also how the cluster connects to each other. And if we, after our assessment, if we notice a region has a very large risk of regional dynamic issues, well, that information will inform efficient conduction of time domain simulations. We can get into time domain simulation and see exactly how bad it is and if any measure is needed to improve the regional frequency dynamics. So this is one of the examples we did. This is on the synthetic Texas system available through the Texas A&M University. On this system, our algorithm told us the optimal number of clusters is to be 5, and we actually plotted those generator clusters on this map here on the bottom right. And for each of the clusters, we listed the regional inertia in gigawatt second here, and also the regional SLI. SLI stands for single largest in feet. This can be the largest generator trip in the region, or if this region takes in a lot of power from other regions through a tie line, that's the power on the tie line. And we already noticed that the cluster 5 has a relatively low regional inertia level, but has a very large single largest in feed. And this is a really bad indicator, but we don't want to rely solely on these numbers, because even if we did these clusters, though the clusters are still connected to each other. So we want to take all those connections still into consideration and assess the regional inertia risk with a more comprehensive metric. That's the metric that we developed called M metric. And the way to look at this M metric is, for each of the regions, we calculate the M metrics and plot them in the form of a box plot. For example, for cluster 5 here, shown on the bottom of this map, it might be the highest risk, but we need to verify using our metric. So you can see the way to read this box plot is, if you see the region's box is way up higher than the rest of the system, that's an indication of high risk of regional dynamic issues here. And if you do the time domain simulations for this cluster 5, on the bottom of the Texas system, you can see these light blue curves. Those are frequencies measured in that cluster 5. So it deviates far away from the rest of the system. By contrast, we also did this for cluster 4, for example, and the box plot like this. So compared to the box plot on the top, you can see the 5 clusters are relatively closer to each other. And if you do time domain simulations in cluster 4, you can see the frequency measurement in cluster 4 is much more coherent to the rest of the system than cluster 5, as shown in the top figure. So this is our one of our examples on the synthetic Texas system. This year, we were able to work with our utility member SRP on this inertia frequency project. So there are some more interesting results coming out after the application of this method on a larger scale realistic interconnection. This is on the WEC system, WEC interconnection model supplied by SRP. So here are some key findings. Our algorithm gave 6 clusters in total for this WEC system. 3 of the clusters are in the US, and 3 of the clusters are in Canada. And it has been well known to the industry for a long time that the Alberta area in Canada can be easily excited for oscillations against the rest of the system. And also, if you have a generation disturbance in that area, the roll off in that area tend to be large. And this is also noticed by our algorithm, and we did some time domain simulations to verify that. And you can see the light blue curves and purple curves here. Those are the frequencies measured in Alberta region in cluster 4 and 5 here on top. And the reason we're seeing this again, it goes back to the 2 major factors at play here. The first is there is a limited number of generators in this region, so it has a lower regional inertia. And also this region is very weakly connected to the rest of the system. That makes it easy to have these regional dynamics that are so different from the rest of the system. One very interesting finding, though, in this study is our algorithm, after its analysis, it threw a blaring warning at us saying, in the middle of the US, especially in eastern Wyoming, there is a pocket that you need to look into. You may have very high regional inertia risks. And we looked into it, did some time domain simulations. Here you can see the green curves are after a generation trip of 400 megawatt, just 400. If you know the size for WEC, this is not really a big generation trip. Typically, the largest contingency we study for frequency purposes can be up to 2,800 megawatts. So this event can be easily overlooked for the WEC interconnection. However, this small event actually caused a very high roll-off level in this cluster 3. The highest roll-off we measured in this region is 920 megahertz per second. In a lot of loss of main protections, mainly in Europe, they have a typical setting of 500 megahertz per second, although they can be relaxed nowadays as we have more and more IBRs, but this 920 is a very high level of roll-off. Again, the reason causing this, if you look into more details how this region is connected to the rest of the system, this area sits in the void of the 500 kV transmission backbone, and it has a sparse distribution of inertia in this region. So again, those two causes make this region prone to these high Rokoff, highly regional frequency dynamics to occur. Okay, so a few key takeaways for this inertial regionalization study approach. Inertia is usually not distributed evenly across the system, so most of the interconnections can expect to experience regional inertia issues instead of before the interconnection level inertia insufficiency occurs. And this can be further aggravated if you have an increasing integration of IBRs in a specific location. The inertia regionalization study we did here helps expedite the screening for areas at high risk of regional inertia issues because it avoids the timely conduction of numerous time domain simulations. We will have a better clue what is at play here. We'll have a better big picture about what are the clusters in this interconnection and which ones will be prone to regional frequency dynamics instead of just doing time domain simulation on the largest generation trips. Sometimes the ones that cause the most headache is the smaller ones that you don't even notice in some of the pockets of the system. So system operators and planners are encouraged to pay attention to these regions identified with high risks and conduct further detailed studies, time domain simulations to ensure satisfactory frequency performance is achieved in these regions. And also this kind of studies is recommended to be done periodically because system can change as the inertial distribution can change as the system generation mix evolves, and also the operating conditions, generation dispatch changes. And our algorithm being able to do this very in an expedited way facilitates this kind of sensitivity studies. As I just talked through this inertia regionalization work, another topic where I will also to bring up here quickly is at EPRI we had, in addition to inertia regionalization, we have also other analysis tools and algorithms that also do regionalization. For example, the voltage control area tool and grid strength assessment tools. And those tools, they also form kinds of clusters or groups of generators or buses based on either the admittance matrix or through sensitivity analysis. But in the end of the day, if we have all those clusters available, that tells us the clustering based on different perspectives, whether can it be inertia, frequency, or voltage, or grid strength, there's an opportunity that we can bring them all together and overlay them, and that the information we can get out of this overlay is there could be areas where different aspects overlaps with each other, and there can be pockets where they don't agree with each other. So for these tools, I'm putting the names here. If any of you have questions about this or interested to learn more about these tools, feel free to contact the presenters today, Deepak, Parag, me, or Vikas. The contact information will be shown at the last slide as well. So the idea is to first bring the inertia and voltage control tool together, the regionalization coming out of the frequency and voltage aspects. If you have overlaps, there are opportunities for us to do co-treatment. You can allocate a resource to attend to both the inertia and voltage purposes. But if there are disparities, we can identify critical buses in those dedicated areas to solve critical issues in those regions. And grid strength, they tend to give us smaller spots where there are very low grid strength or short circuit capabilities. In those regions, we want to be avoiding citing more IBRs in those locations and prioritize synchronous condensers and generators. And if you have to put IBRs or StatCom in those areas, write-through capabilities are recommended to ensure safe operations. Okay, these are the topics around the inertia regionalization. And the next thing we'd like to share is the frequency response deliverability. This is still very much connected to the first topic because in areas, regions that have very low inertia levels and weak connection to the rest of the system, if you have a very strong IBR response in that region, stability could be a concern because you now have a very strong response, not only strong, but also fast response. As Deepak just mentioned, faster is not necessarily always better. And especially having low inertia in the region, there's a larger chance that the IBR response can interact with the local rotating mass, or even the interaction can spread out to the whole system and cause inner area oscillations and instabilities. So what we have been observing is for these fast responding resources, if you place them in one locations, it may improve the frequency response, the stability very well. But if it's located in another location, sometimes you can see instabilities. And the reason causing that, as mentioned, if the fast response is provided by IBRs through a weak connection and from a weak region, those instability can arise. That's why we are developing this method to, in order to do fast stability screenings. And the idea behind this is very closely related to the regional inertia topic I just mentioned. We used still takes in the similar swing equations for generators across the whole system. This includes the information about how these rotating masses are connected, how they tend to interact with each other. But on top of this, we still need to include the response of the IBRs into this state matrix. And once you have both the generator dynamics and IBR frequency response in this approximate state matrix, we can do eigenanalysis to see to screen for instability scenarios. And there are majorly three factors at play here. One is the regional inertia level, and the other is the connection strength of the area to the rest of the system. And the third one is the response characteristics of the IBR resource that's providing the frequency response. So the application of the algorithm will give some figures like this on the left. It'll show you an eigenloci as you change some of the parameters in the IBRs or the system configuration. For example, here I'm showing as we tweak the droop gain of the IBR providing frequency response, the algorithm will tell you if you have a too high of a gain crossing a certain value. For this case, it is droop gain of 98. You can expect to see oscillations, instability. So with the oscillation frequency of a certain level, in this case, it's 1.35 hertz. Doing this, we don't have to do numerous time domain simulations again. The goal is to do a fast screening to give us a better sense where might be the riskiest region that we need to be mindful. And the time domain simulation shown on the right is for the validation purposes. You can see when the K, the droop gain increases to 95, it becomes a sustained oscillation, and the oscillation grows if you pass that marginal situation. And one caveat to this ongoing work is this formulation, the state matrix, it does not capture all dynamics. It captures only the electromechanical interactions between the generators and also the IBRs. And the goal of this study is to expedite the stability screening and inform further detailed time domain simulations when necessary. So this slide shows a few higher level critical things. One is what are the factors that I just mentioned, this inertia, connection strength, and IBR frequency response characteristics. And these factors will result in different kinds of oscillations. The major two types that we observe is one, the local oscillations. That's mainly because if you have a very low inertia region with a very high IBR penetration and use those IBRs to provide a very strong frequency response, if you have a weak connection to the rest of the system, you can have purely interactions between those local generators and the IBR. But in other situations, if you have a relatively larger inertia, but still there's a risk for inter-area oscillations when this IBR assists participate in the potential inter-area modes already existing in the system. All right. This is the third topic I would like to share with you. It's a collaboration between EPRI and our member SRP. We covered a lot of topics related to what I presented in previous slides. There are inertia, there are frequency response, there are all aspects, a lot of interesting results coming out of this project, so we would like to share them with you all. First, a quick introduction about our utility member SRP, Salt River Project. It is a community-based, not-for-profit organization providing reliable, affordable, and sustainable water and energy to more than 2 million people in Central Arizona. And SRP, the reason we initiated this effort is the SRP seeing rapid integration of IBRs in the recent years. Before 2023, there are about 450 megawatts in solar and BESS batteries combined. But by the end of 2023, they already have about 1,200 megawatts. And by the end of this year, this number will increase 25, almost double, to 2,500 megawatts and more to come in the following years. So even though SRP system is geographically very tight and robust, serving the Phoenix metropolitan area, and therefore they're not seeing significant frequency issues to occur in the next few imminent years. But there is still a large gap in the SRP's knowledge that deserves attention for their customers and their participation in the wider Western interconnection. So in this project, we mainly look at a few topics. One is to assess if you have a rapid integration of IBRs in the system, what that can do to the frequency performance, both for SRP and for the WEC interconnection. And the second, in those high IBR penetration scenarios, we can no longer treat the IBRs as purely just the troublemakers, because they are now the predominant resource. We have to rely on them to provide frequency support in turn, not just making troubles. So we try to understand in this study how IBRs can be used for fast frequency support and how we can parameterize to provide better performance if they're capable of that. And lastly, we want to compare the performance of different resources. That includes how the IBR compared to, say, synchronous condensers in providing frequency response. And even within the IBRs, what are the differences between grid forming and grid following inverters? And this has been a very hot topic recently, the grid forming technologies. We're also going to cover some of that. So first, what the integration of IBR can do to frequency performance. In our study, we started with the base case supplied by SRP, where there is a 17.5% of renewable penetration for the whole WEC system. And we created a number of scenarios. And in the end, the highest penetration scenario here is shown on the right, the IBR penetration of 69.6%. That's almost 70%. And both the ROCOF, the rate of change of frequency, and that's indicated by the insufficiency of inertia, and also the frequency nadir deteriorated significantly. The ROCOF increased from 600 to almost 1700. And the frequency nadir is getting closer and closer to the under frequency load shedding to the point where it only had 8 millihertz of margin. It's almost touching the UFLS threshold, but in the base case, it has about 230 millihertz from the UFLS. So we can expect to see a significant change in frequency dynamic in the system if you have a large number of IBRs replacing the synchronous generators, in assuming they are not providing frequency support. But in power systems like the one on the right, where you have 70% of penetration, as I said, we have to use these IBRs to provide frequency support. And we did a lot of sensitivity studies, and here is a quick example of what IBRs can do in supporting frequency. Because in our study, we're using this very conservative scenario because we don't really know what the situations can be outside of our members' utility footprint. We don't know other utilities, how they are going to manage their IBRs and allow them to provide frequency response. So we're assuming only the IBRs in the SRP area are providing frequency response. This is a very conservative study, but still, even with just a few IBRs within the SRP region, we still see a very big improvement in frequency response. But originally, before we parameterized the IBRs, as I said, the base case had an 8 millihertz of margin from the UFLS threshold. It's almost touching it. Before we parameterized the IBRs, after we enable the IBRs frequency response, the margin increased from 8 millihertz to 21 millihertz, and not a big improvement. But we realized that now that we're using these resources that are capable of providing response much faster than traditional generators through their governors, why don't we parameterize to provide a stronger and faster response? And that's what we did. And just using a few IBRs within SRP, we were able to provide a margin of about 100 millihertz with only a small headroom within SRP. And this improvement can be explained by this figure. This figure shows the power output for this frequency response coming out of different regions. The blue is the outside of SRP, the rest of WEC system, where most of the response are due to the traditional generators frequency response. And the red curve is the summation of the power in response to frequency deviation from within the SRP, and they are all from energy storage IBRs. And one number I would like to point out is these IBRs they had only 2.5% of the total headroom across the WEC. So it's a very small portion because SRP just was a small portion of the WEC interconnection. But during the transient, the highest percentage of frequency response coming out of these SRP energy storage devices reached about 42%. And you compare the number 42% to 2.5%, it's pretty unfair for SRP to take that much responsibility for the WEC. But that's not the intention of the study. The idea is to show how much IBRs can help with the frequency response. What these SRP IBRs are doing here is really to buy time, by this very important period of time for the generators outside of SRP to be able to have a chance to ramp up their output and stabilize the frequency of the whole interconnection. If we don't have this very fast response from the SRP battery storage systems, the frequency nadir can drop very fastly in the first few seconds when the generators still are trying to ramp up. But in the future, in reality, we will have frequency response from IBRs outside of SRP. Once we have that, we can expect to see even better frequency dynamics because now we have a larger pool of IBRs that are capable of the same fast, strong response to the system. So another thing we explored is the comparison of different responses. I talked a lot about IBRs providing frequency response. They are able to provide very fast, much faster response than traditional generators, and the response can be sustained for a period of time. And now we want to compare how these IBRs could contribute differently from the other traditional resources, say synchronous condensers, because as we retire a lot of generators, sometimes it makes economic sense to convert some of the generators to synchronous condensers. They can contribute to voltage support, that they can contribute to grid strength. And if we already have synchronous condensers, it might be good to explore also using them for frequency support. And what we found, the key takeaway here is synchronous condensers mainly helps with roll off due to the built-in inertia. It's very effective at that. But if you look at the frequency nadir with these synchronous condensers, it almost doesn't change that. That's because the synchronous condensers, the release of energy from it is not sustainable. It's only in the first few moments when frequency declines very fast, the inertial energy is released. But past that, it's not a sustained release, so the frequency nadir didn't change. On the other side, the IBRs, they were not as effective as the synchronous condensers in limiting the roll-off because they are not absolutely instant response as those physical rotating mass, but they are very effective in arresting the frequency nadirs. If you look at the blue curve here on the left, that's the IBR providing faster frequency response. They actually provide a much better frequency nadir than with synchronous condensers. And as I said, even within IBRs, there are so many different kind of controls. You have GFM, GFL, and it's a very interesting topic to a lot of people, how the GFM and GFL can differentiate from each other in providing frequency response. We also did some studies recently on that. I will give the floor on to my colleague Deepak to give you more detail on that. Deepak?
Yeah, thanks, Sam. So essentially, we've been trying to look at now if you have different types of inverter-based resources in the system and just getting to an understanding of how is this frequency response going to be impacted based upon these configuration of these resources. Because there is a question that keeps coming up is, okay, is this frequency decline that we are seeing, is it because of the type of inverter? And is there something that we can do based on that? What we really identified is that, it's the first few cycles that matter or that have a change in the response that comes up. You can have a non-grid forming device parameterized in a way to provide fast frequency response, to provide frequency response at the inverter level. And what you would end up seeing is in these first few cycles, in these first 100 milliseconds is where you would see the difference in the energy injection that is coming up between a grid forming device and a non-grid forming device. But after that, pretty much the response is quite well aligned. Of course, it does depend upon the parameterization that you would have. So then the question then becomes is if you are going to be looking at these kind of resources, it's important to keep it in perspective because maybe it may not impact the nadir so much. So there may not be too much of a difference in the frequency nadir, depending upon whether you have fast frequency response or whether you have a grid forming resource. But what may be the difference is those rate of change of frequency that might occur in the first 100 milliseconds, and especially if there is a loss of mains protection. It's not from the perspective of rate of change of frequency impacting UFLS. That is an entirely different kind of criteria. And if you have fast frequency response, the UFLS is not necessarily impacted, but only if there is some form of a loss of mains protection that might get impacted, that can be something to look at. All of this comes down to energy reserve. It comes down to having enough energy available. And if we go to the next slide, we'll kind of little compare about how does this come about. So if you actually take a look at synchronous machine plant and a synchronous machine, so the red curve is a synchronous machine plant, the purple curve is a synchronous machine itself, you kind of see that the machine inertial energy injection is for the first 100 to 200 milliseconds. After that, the governor starts kicking in. So you are essentially only looking at that point in time to get an understanding of the difference. And then if you compare that with grid forming versus non-grid forming, but say with some form of fast frequency response, you can dig a little bit deeper and see maybe for the first 50 milliseconds, or first 3 cycles, 4 cycles, that actually you see a difference between the resources. But after that, they pretty much catch up quite well. going to the next slide, you can get a little bit more insight into how these actually impact the system. So if you actually consider a system and see a 6% increase in load in this low inertia system, then if you look at it on the broad strokes level, if you look at it at the high level, you actually see very similar performance in frequency, irrespective of whether you have grid forming or whether you have fast frequency response or so. Now, if you dig into the details, so if you look firstly at the first 1.5 seconds, you do start seeing that there is a little bit of a difference in the response between these various resources as shown on the right-hand side of the figure. But if you actually look at the frequency, then again, you have to zoom in quite a bit to look at the difference. And then if you actually zoom out and look at the nadir of the frequency response, they quite align well. So what does all of this have to do with the frequency response of an interconnection with the varying percentage of inverter-based resources? It comes down to energy. It comes down to how much energy one wants to inject and at what point in time should that energy be injected. So if you look at the next slide, we can break this up a little bit to try to understand the energy injection. So just looking at that instant of the disturbance that occurs, if you look at the first 3 cycles after the disturbance occurring, then a synchronous machine and a grid forming resource in this particular configuration and system provides around 0.03 kilowatt hours of energy injection, more than what a non-grid forming resource would do. But that's only in those first 3 cycles. If you look at it over that entire 1 second of response that is there, then they all provide a similar amount of energy. In this case, it was 2.2 kilowatt hours of energy being injected by these resources. So what we have to ask ourselves a question is that as we have more of these inverter-based resources coming in, as we start looking at results that look at frequency response, it's important to ask ourselves what assumptions are made. What is the assumption made on the speed of response from an inverter-based resource? What is the assumption made with respect to how much frequency response an inverter-based resource is providing? Is the inverter-based resource even providing frequency response or not? Does the inverter-based resource have the capability to provide frequency response? How much energy is being injected by that inverter-based resource, and in what time frame is that energy being injected? All of these questions have to be answered before making a determination of whether a frequency response of a system is good or bad, depending upon the type of inverter-based resource that's there on the system. And all of this leads back up to some of the work that we did on trying to identify what point in the system, at what location in the system, can you inject a certain amount of frequency response or not? Can that fast frequency response be fast enough or not? Is there a regional inertia cluster that will result in one having to look into local disturbances in more detail rather than the global interconnection-wide disturbances? With that, we can go to the next slide and close out. I think there's a lot of questions that have been coming in. So we'll keep the slide open here. We don't have to, we've spoken about a lot of them. Do want to acknowledge a lot of the collaborative work that we've done with Salt River Project and the engineers at their end in taking the study along, showing the initiative on trying to understand more on how do these inverter-based resources really impact frequency response and what kind of performance should they be asking from their inverter-based resources in trying to improve the performance of the system. With that, back to you, Julia.
All right. Yeah.
Great. Thanks so much. There are a lot of questions, so I think we'll get to hit only on the most popular ones. So the first question I think was answered during the presentation, but I'll just give you a minute if you want to add anything. How does the approach account for impact of fast frequency response facilities within each region, impacting the dynamics of frequency in each sub-region? So this question came basically after you presented the first part on inertia estimation in each region.
So it's essentially, I guess, with respect to identifying the regional inertia clusters to a certain extent, and so
yeah.
Yeah, Parag, go ahead.
Yeah. So it does not. So it does not take into account the fast frequency response. The way you want to think about it, right? Inertia clustering right now, it's looking at how rotational inertia is decreasing in your system. Now, fast frequency response, that is sort of a remedy to rotational inertia, right? So when you're doing this transition, when you're going from an all synchronous machine system to sort of this system where you have inverter-based resources where you may or may not have the provision to provide fast frequency response. This type of tool allows you to identify clusters where you really want to start thinking about, I need to put in fast frequency response. So that is the approach that we have taken to identifying this regional inertia risk. Now, that said, as we move into the future and we are going to have a lot of inverter-based resources, which is going to dominate, which I think was one of the second questions, what about 100% inverter-based system? We have to go and rethink this particular metric. We have to do things differently because maybe the challenges during that time will be slightly different than what we look at right now with at least with inertia and frequency matter.
Right. Thanks, Parag. Then I guess I'll skip this next question about 100% converter-based system because you already answered. Let's go to the next one. System dynamics are usually contingency specific. Does the proposed grouping depend on contingencies?
Yeah, the grouping doesn't depend upon contingencies, but the risk depends upon within each cluster what is the possible largest loss of generation in feed. And that is what we call SLI, single largest in feed. So all it has to be is the largest credible outage. It doesn't mean that it's going to be the outage of a single generator or a single plant or a single HVDC link, but it could be whatever is your credible largest in-feed loss. And you can go back and look at your historical data, or you can look at your protection arrangement to figure what that could be, and that's how that is defined.
Right. Next one, how are the regional clusters defined? What is the criteria used to select which generator is included in which cluster group?
So the short answer to that is the algorithm tries to look for the electrical closeness of generators together. And it's not just the electrical closeness, it's actually the electrical closeness, which is defined by the susceptance divided by the inertia. So it's sort of that ratio of the electrical susceptance and the inertia. That is what is being used to identify which groups are together and are expected to have sort of a coherent dynamic when you have this sort of frequency event.
Right. The next one is why the rock-off was measured over 0.1 second time. Any filter used for the frequency measurement to be that smooth after the disturbance?
Yeah, the short answer to that is when you measure rock-off on bus, you're measuring the rate of change of angle. Angles are not state variables, so they tend to change very quickly. Normally, when you're measuring rock-off, you want to measure something based on which you're going to take any sort of an action. So it could be a protection action or any kind of action. Typically, 100 millisecond or a 500 millisecond threshold is chosen because that is kind of what the filtering exists in most protection devices. So that's why the 0.1 second was used. That said, it's not that 0.1 second is a standard. It could be 0.1, it could be 0.5. Different jurisdictions have different ways of looking at it.
That's good. Thank you. Can short circuit ratio screening be correlated with regional inertia screening?
Yeah, that's one of the future goals. And we have a slide on that where we talk about how we should be leveraging all of these things together. So definitely intuitive, and yeah. So yeah.
And the idea there is it may not, the screening itself may not link up the two different concepts, but it can help identify if you want a source to help with improving system strength, does that same source also need to help with improving inertia injection, need to help with other stuff? So you can use these different screening methods to get an understanding of what is the commonality of the services that you want at that particular location.
Sounds good. Thanks. I'll hit one last before we close out. Apart from the simulations, what kind of mathematical calculations were performed to understand or observe the effect of FFR on the grid stability and response?
So we did not really do any analytical solution. At least in my mind, there isn't an analytical way of judging all of this. But that said, some of the screening methods do use analytical techniques to do the screening. So there is some math that goes behind it. I'm not entirely sure if I answered your question or if I really understood the question properly, but it's a mix of both. There is some analytics that goes in and there is some simulation that goes to confirm what we are observing in the analytical solutions.
Yeah, and if the question was not sufficiently answered, I will just ask whoever posted the question to maybe put another one to clarify. Just in the interest of time, we're almost at the top of the hour, so I will need to wrap it up. I would like to thank Parag, Deepak, and Chengwen for this really informative presentation, and the audience for your attention and great questions, a lot of questions that you'll have to answer offline, sorry. As I mentioned earlier, the email will go out once the video file has been posted, and we'll answer the questions we didn't get to and get them posted as quickly as possible. The next webinar will be a joint GPST ESIG webinar on diagnostics and mitigation of observed oscillations in IBR dominant power systems, a practical guide that just been published by ESIG. And the webinar is coming up tomorrow, so we have a bit of a crunch of webinars this week, and will be presented by Nick Miller of Hickory Ridge, who was the main author of the guide. For more details, including registration, you can look at our webpage at www.esig.energy. I would also like to cordially invite you to attend our upcoming ESIG Fall Technical Workshop on October 21st through 24th in Providence, Rhode Island. So further information on all our webinars and meetings can be found on our webpage under events, in our newsletters and information emails, and you're all invited to attend. Parag, Deepak, Chengwen, thank you so much again for coming today and presenting, and thank you all for your interest. We look forward to seeing you again in the near future, and in the meantime, everyone take care, stay safe, and thanks for your participation. See you soon.
Thank you. Bye.